Imagine you're trying to find your way through a massive, sprawling maze. A classical computer, the kind in your phone or laptop, would try one path, hit a dead end, go back and try another. It would do this incredibly fast, but it's still a one-at-a-time process. Now, what if you could explore every single path in that maze all at the same time? That is the astonishing promise of quantum computing. It's not just a faster version of what we have today. It's a completely different way of thinking about calculation itself. One that harnesses the wonderfully strange rules of the universe at its smallest, most fundamental level. It's a technology that could solve problems we currently consider impossible. This new kind of computation is born from the world of quantum mechanics, a realm where particles can be in multiple places at once and can be mysteriously linked across vast distances. For decades, these ideas were the stuff of theoretical physics, scribbled on blackboards in university halls. But now, brilliant minds are building machines that use these bizarre properties to compute. This isn't science fiction. It's a global race with tech giants like Google, IBM, Microsoft, alongside countless university labs and startups. The implications are staggering, promising to reshape everything from medicine to materials science. Why does this matter so much? Because the universe at its core is quantum. A quantum computer speaks the universe's native tongue. This isn't just an upgrade, it's a paradigm shift, a new tool for humanity to understand the cosmos. At the heart of your smartphone is a tiny switch called a bit. This bit is simple and dependable. It can either be a 0 or a 1, off or on. All the incredible things your phone does are built upon billions of these simple binary choices. The quantum world, however, plays by different rules. The quantum equivalent of a bit is called a qubit, and this is where the magic begins. A qubit isn't restricted to being just a 0 or a 1. It can be a 0, a 1, or a combination of both at the same time. Think of it like a spinning coin. While it's in the air, it's not quite heads and not quite tails. It's a blend of both possibilities. Only when it lands, or when we measure the qubit, does it collapse into a definite state. By existing in this superposition, a single qubit holds more information than a classical bit, and when you link qubits together, their power grows exponentially. 2 qubits can represent 4 states at once, 0001, 1011. 3 qubits can represent 8, and so on. With just 300 qubits, you could represent more states than there are atoms in the known universe. There's another strange property called entanglement, which Albert Einstein famously called spooky action at a distance. When 2 qubits are entangled, they become intrinsically linked. Whatever happens to one instantly affects the other, no matter how far apart they are. If you measure one entangled qubit and find it's a 0, you will know with absolute certainty that its partner is a 1. This creates shortcuts through problems that would take a classical computer billions of years to solve. It's a cosmic dance choreographed by the laws of physics, offering a completely new way to process information. Creating and controlling a qubit is an immense engineering challenge, and scientists have devised several ingenious ways to do it. There isn't just one type of qubit, there's a whole menagerie of them, each with its own strengths and weaknesses. One of the most common types is the superconducting qubit. These are tiny electrical circuits cooled to temperatures colder than outer space, about -273 degrees Celsius. At these extreme temperatures, the circuits lose all electrical resistance and begin to behave quantum mechanically. Companies like Google and IBM have used these qubits to build some of the most powerful quantum processors to date, as they are relatively fast and easy to build. Another leading contender is the trapped ion qubit. Individual atoms are stripped of an electron to become charged ions, and then held in place by electromagnetic fields inside a vacuum chamber. Lasers are used to manipulate the quantum state of these ions, effectively turning each atom into a near-perfect qubit. Trapped ion qubits are incredibly stable and have high fidelity, but they are generally slower compared to their superconducting cousins. Then there are photonic qubits, which use single particles of light, photons, as their information carriers. The quantum state can be encoded in a photon's polarization, the orientation of its light wave or its path. A key advantage is that photons don't interact much with their environment, making them less prone to losing their quantum information. They can be transmitted over long distances through fiber optic cables, making them ideal for quantum communication and networking. Startups like PsiQuantum are working to build massive photonic quantum computers, aiming to use light itself to solve intractable problems. Each technology represents a different bet on how to best build a quantum future. The race is on to see which design can scale up to millions of stable qubits while keeping errors at a minimum. One of the greatest enemies of quantum computing is a phenomenon called decoherence. Qubits are exquisitely sensitive. The slightest vibration, a stray magnetic field, even just a change in temperature can disturb their delicate quantum state. It's like trying to get that spinning coin to land on its edge. The smallest breeze will knock it over, leading to errors in calculations. This fragility is the single biggest obstacle to building large-scale quantum computers. But what if there was a qubit that was naturally protected from these disturbances? This is the holy grail of quantum computing, the topological qubit. Unlike other qubits that store information in local properties of a single particle, a topological qubit stores information globally in the very fabric of the material itself. The information is encoded in the way certain exotic particles, called quasi-particles, are braided around each other. To corrupt the information, you would have to disturb the entire system at once, making it intrinsically robust and immune to local noise. It's like trying to change the meaning of a sentence by nudging one letter, but the sentence magically rearranges itself to preserve its original meaning. The key lies in finding Majorana fermions, bizarre particles that are their own antiparticles, first predicted by Ettore Majorana in 1937. For decades, they were purely theoretical. But recently, physicists have found compelling evidence of Majorana zero modes at the ends of special nanowires made from superconducting and semiconducting materials. The version found in these systems is called Majorana 1, referring to the first confirmed signatures of its existence. If they can be reliably created, controlled and braided, it would represent a monumental leap forward, a truly stable and powerful quantum computer that's far less prone to errors and much easier to scale. So, what will we actually do with these incredible machines? Their greatest impact will be in areas where complexity overwhelms even our best supercomputers. One of the most promising applications is in medicine and materials science. Designing a new drug or catalyst involves understanding how complex molecules interact. Simulating these quantum interactions is perfectly suited for a quantum computer. We could design life-saving medicines, hyper-efficient batteries, revolutionary solar panels. Another major area is optimization. Imagine finding the most efficient route for a global shipping fleet, managing city traffic flow in real time, optimizing financial trading strategies. These are colossal puzzles with mind-boggling variables. Quantum computers could find optimal solutions in a fraction of the time, revolutionizing logistics, finance, and AI. But will you have a quantum computer in your home? Probably not. At least not like our laptops today. Building and running a quantum computer is an extraordinary feat of engineering. They require vast amounts of rare materials and superconducting metals. They must be housed in large, shielded facilities with cryogenic refrigerators that cost millions. A single dilution refrigerator can cost upwards of £500,000. For the foreseeable future, quantum computers will be like today's supercomputers. Massive, centralized resources accessed via the cloud. The quantum revolution is not a distant dream. It is happening now. It is a journey to the very edge of what we know about the universe and challenges us to become masters of the quantum realm. While the path is paved with immense hurdles, the potential rewards are boundless. We are at the dawn of a new age of computation. The universe is far grander, stranger and more wonderful than we ever imagined, and quantum computing is our key to exploring it.